To the channel of Engineering Chemistry Lab Videos. Myself, Dr. Kiran Kumar P, Assistant Professor at ATME College of Engineering, Mysore. Today's experiment is the determination of pKa of a given weak acid using pH meter. So the aim of the experiment is to determine pKa of a given weak acid using pH meter. So pKa is the number of, it is a number that describes the acidity of a particular molecule. So the lower the pKa value, greater is the strength of an acid and greater its ability to donate its proton, to dissociate. Strong acids undergoes complete dissociation, hence the study of dissociation constant is of no use, whereas the weak acids undergoes partial dissociation. If you look into the two equations, HCl, which is a strong acid, it completely ionizes when dissolved in water, whereas the acidic acid, it is a weak acid which partially ionizes when dissolved in water. Hence, pKa value is measured for weak acid. So therefore the study of ionic equilibrium and the calculation of Ka is applicable only to weak acids. So we generally calculate the dissociation constant only for weak acid. For example, acidic acid, it is a weak acid as shown in the earlier equation, which partially ionizes when dissolved in water. So this is an acidic acid. When dissolved in water, it partially ionizes in water. Hence, the dissociation or constant of weak acid is required to measure. Since the dissociation constant of a weak acid has small value, another parameter was introduced called as pKa, strength of weak acid, power of dissociation constant of weak acid. So pKa is determined by measuring the changes in pH. So by measuring the changes in a given sample, we measure the pKa. According to the Henderson equation, which is given by pH is equal to pKa plus log of salt by acid. You look into this particular equation, which is an Henderson equation. pH is equal to pKa plus log of salt by acid. Here is a weak acid, acidic acid. When it is titrated with NaOH, we get the product sodium acetate, which is a base, which is a salt, right? This is a product salt, acid, right? So according to this equation, you check into this reaction over here. At end point, only the salt will be formed, right? Only we have salt, but not an acid. So pH is equal to pKa plus log of salt. At end point, the equation will be pH is equal to pKa plus log of salt. Similarly, for strong acid, right? Now, here at what point pH will be equal to pKa? As I said, pKa is measured by measuring pH. At end point, only salt will be there, but not a acid, right? So by looking into this equation, at what point pH will be equal to pKa, right? If I say it, when salt is equal to acid, what is salt? The product is equal to the reactant. Salt is equal to acid. pH will be equal to pKa, right? At half equivalence point. Equivalence point says when completely the acid is neutralized, when completely the salt is formed, we call it as equivalence point. So that will be the equivalence point, EP. At equivalence point, only salt will be there, right? Say for example, equivalence point is 4 ml or 4 cm cube. Exactly at half of this reaction, half of the reaction, the salt formed will be equal to acid. How to find this half equivalence point? By finding equivalence point, which is divided by 2, it will be 2 ml, right? So 2 ml is the half equivalence point. By measuring half equivalence point, we measure at half equivalence point, pH will be equal to pKa, right? So this whole part will be 0. How? Salt is 1, acid is equal, so log 1 becomes 0, right? At half equivalence point, pH, whatever the pH measured, will be equal to pKa. Now in order to measure half equivalence point, we need to measure equivalence point. Let us see the experimental demonstration followed by the tabulation. This is a tabulation part. So you can see here volume of NaH added in cm cube from burette. pH is recorded using pH meter. So this is the instrumentation part. We need pH meter. We need ion selective electrode, that is a glass electrode which identifies H plus ions, a beaker, magnetic bit, magnetic stirrer, and a burette with stand. We need pipette. We need a given weak acid, standard NaOH, and distilled water. Initially, wash the beaker with distilled water and also the electrode. Pipette out 50 cm cube of given weak acid into a beaker. (50 cm cube), you need to pipette it twice. Each pipette is of 25 cm cube. So pipette out weak acid 50 cm cube into a beaker. Now fill the burette by standard NaOH. Standard NaOH. Up to 0. Place the burette into the stand. Now immerse the electrode. Switch on the instruments, pH as well as the magnetic stirrer. Fix the RPM level. Immerse the electrode. Make sure it is not completely dipped so that there will be a damage on the electrode. Note down the initial reading. Initial reading is 3. For 0, initial reading pH is 3. Right? Add 0.5 increments. pH will be increased. The reason is your acidic concentration is gradually decreasing due to formation of sodium acetate, that is the salt. So acidic medium is decreasing, hence pH will be increased, right? So after each addition of 0.5 ml of NaOH, sodium acetic acid is converted into sodium acetate. As a result, pH will be increased. So after each addition of 0.5 increments of NaOH, note down the pH values. So after each addition, you may see the pH is increasing. This increase is due to the neutralization of acetic acid. Right? So there will be a point where completely the given acid is neutralized At that point, there will be sudden jump in the pH. So that sudden jump is due to the complete dissociation of acetic acid to sodium acetate. So once you get sudden jump in the pH, take 4 to 5 readings by adding 0.5 increments. Note down the respective pH. Now pH is 5. You can see from 5.8 to it has been sudden jump in the pH to 12.53. So this is an equivalence point which shows the complete neutralization. 4.5 is the equivalence point. When you reach 4.5 ml, so all acidic acid will be neutralized to sodium acetate, I mean the salt and water. Further, you take 3 to 4 readings. So 4.5 you get a jump. Here it was 5, here it was 12. Now, this is a graph. You can see here the graph is plotted for delta pH by delta V. We call it as first derivative curve. Delta pH by delta V versus volume. Right? When you plot a graph of delta pH by delta V versus volume to find out equivalence point. So this is a jump here. There is a jump here. Right? When you reach 4.5 ml, the pH was suddenly increased. Right? So this is a jump. So this is equivalence point. Equivalence point is what? It is a end point where acetic acid is completely neutralized to sodium acetate. Now, with the help of this equivalence point, again plot another graph of pH versus volume. This is the equivalence point. 4.5 is the equivalence point. With the help of equivalence point, you find out the half equivalence point as already explained in the Anderson equation, right? 4.5 you get 2.25 somewhere here. Okay. So pH at half equivalence point. Half equivalence point is 2.25. pH at half equivalence point, this particular point is your pKa, right? So this is a equivalence point 4.5. 2.25 is the pKa value. 2.25, the pH, whatever the pH observed at 2.25 is your pKa. So pKa value is 4. Note down the results. Equivalence point 4.5. Half equivalence point is 2.25. Equivalence point divided by 2, it's 2.25. pKa is the pH at half equivalence point, that is 4.